Hi, I'm really happy to bring you my first sort of technical evaluation video. I'm going to look at current sensors and reed switches specifically with regard to detecting trains on your layout. My focus is toy trains, but everything I'm going to talk about applies to model trains as well. And I hope you enjoy the video. I plan on doing maybe 2 or 3 of this type of video a year, probably starting next November. So subscribe if you want to catch the next one. Okay, thanks, bye. As was mentioned in the opening, this is about detecting toy trains with Arduino and other microprocessors and model trains as well. We want to use a microcontroller, we want to do it reliably, we want to keep the wiring simple, and we want to keep the programming simple, and of course we want to keep the costs down, particularly if we're ending up putting a lot of sensors on the tracks. We can do this with light, we can do this with current, we could do this with switches. We could do this with cameras. I'm really going to focus on switches and current in this video. We're going to talk about light sensors briefly, and then we'll focus on current sensors in some detail, and then finish up with reed switches. Light sensors often come in an emitter and receiver pair. IR or visible light can be used. Visible light is more tricky. You can use laser sensors, which are often rangefinders. The big challenge here is mounting these types of sensors, often requiring changes to bench work and track. In the next few experiments, we'll use this setup where we have 2 current sensors on the board, as well as an Arduino power supply fed by a Lionel transformer. So you'll see this in the next few videos. The 2 current sensors we'll experiment with today is the ACS712 and the MAX4080. In particular, it's the 4080S. But the first one, the ACS712, is a Hall effect sensor, which basically means it uses the magnetic field generated by the current moving through the wire. These generally will work with both AC and DC since they're just measuring the magnetic field. And because of that, they can be impacted by nearby magnetic sources. Possibly Magne-Traction, and we'll take a look at that, see if that's the case. We'll also look at one of these shunt-based sensors, the MAX4080. I mentioned the INA 169 from Adafruit because I've deployed that on my layout, not for train detection, but for other purposes. And it behaves almost identically to the 4080, except it's more versatile. So it's easy to tune to your current needs. So that's really the only main difference between those two. You could potentially hack the 4080, but it's easy to do that with the INA 169. These work by really dividing the current or voltage, if you will, and then amplifying this very tiny bit of current that is coming into it. So your circuit is not isolated from the circuit you're sensing, but because the resistance it's passing through is so high, it is almost effectively isolated. So you have to take that into account. And for this reason, they're usually limited to DC circuits. If you're going to use current sensors, you need a block of track that's electrically isolated from the rest. And we can do that using plastic pins or cutting the rails with a Dremel, creating an air gap. In any event, you're going to run wires to power this electrically isolated track that are separate from the other. And you can put your current sensor anywhere along that run of wires. Now, it's important to note with a shunt-based sensor, which is typically only going to work with DC, and therefore maybe doesn't apply here, that has to be wired on the positive side. And if you use a Hall effect sensor in a DC situation, that should be wired on the negative side. However, in the case of a Lionel train, which is typically going to be AC, you are more or less limited to Hall effect sensors. And in the case of AC, it doesn't matter which side. Anywhere along that either wire will suffice. What happens is when the train comes onto the block, then the current is drawn through those wires that power just that block. And that's how the current sensor works. It detects that current flowing through those wires going to the block. And that's really all it is to it. But, in summary, if I'm in a Lionel situation, I'm limited to a Hall effect sensor in most cases. And then I'm going to wire that, probably not right really close to the track so I don't get interference from the motors or Magne-Traction. And I'm not going to put it really close to the transformer since it's a potential source of electromagnetism. I just, for safety's sake, I'm just going to move it at least 3 inches or more away from the transformer. Other than that, I'm going to keep my eye out for other magnetic sources if I'm using a Hall effect sensor. Okay, what we have is AC power going into AC-DC converter, going to a current sensor, going to a motor. This motor is a Lionel track inspection car that has been deconstructed. It runs on DC only for my use and also this test. So what we'll do here is, you see we've got the amperage reading here in DC on the voltmeter. We will apply power and see where that goes. We get a reading of 33 milliamps. And that's that. And then I'm going to turn it off. And we'll move the camera to look at the screen that we just reduced. So reading the current sensor, we see we've got around 33 with some variation. When we look closely at these two graphs, we see there's a bottom portion in red. That's the voltage reading. And then that is mathematically transformed into the current reading above in black. And when we look at it carefully, we see that sort of middle ground is 34 milliamps, which is just a little higher than what we got from our multimeter. The other thing to notice is that because there are only so many bits of information we're reading on the port, that the noise is, a few milliamps. And that'll become even more important when we look at the next sensor. But keep that in mind. We have enough bits that our noise is 2 or 3, I'd say 4 to 8 milliamps. That's what we're talking about. So that can be important to whatever your application you're applying it to. For sensing trains, it's a pretty dramatic and easy to tell difference between the train running and not. And I also did a test with this sensor where I add load, and indeed the current usage increases, and that's easy to see with this sensor as well. Okay, next up is our ACS 712 Hall effect current sensor. And remember, this works by detecting the magnetism produced by the current flowing through it. This particular unit has the magnetic sensor built into the circuit, so you connect a line you're sensing to this sensor. Many others you will see on the market have like a ring that you put the wires through or wrap them around, but they work in exactly the same way. It's just this has that wraparound circuit built into the circuit board. Okay, here's our experiment. We just turned on the power. We're running our little track inspection car over there on top of the white bucket. Our meter's showing us it's 32 milliamps. That's what we expect to get out when we look at our results for steady state running. Then if we add a load to those wheels by just pressing our finger on it, you see the amount of energy it takes to keep them turning goes up. That went up to a little over 50 milliamps. And so that's that part of the experiment. Next, we'll move on to the Magne-Traction, or the magnetic experiments. Very magnetic. Anyhow, so there's a tiny little magnet, and which is actually pretty easy to mount on the bottom of a train if you want to use magnets. But there we go. We get that magnet near the sensor, and of course that doesn't generate any amps at all. So we'll come back and we'll look at the graph and see if it did anything at all to the sensor. Does the sensor care about a little magnet like that? It's a good question. Now, we got a little Magne-Traction. It's a 1950s vintage Lionel locomotive. And there you go, the test, that wheel, it has a little magnetism to it. Not as strong as that little magnet. We start out high, we go low. We go to within about 1.5 inches of the sensor. Really not much closer than that. The output from the sensor converted to milliamps gives us this trace. And as you can see, the section labeled magnet is dramatically higher. We're getting dramatically higher signal, even though there was no current. And Magne-Traction also produced a really high signal. So high, in fact, it's hard to see where the signal produced by the load, the steady state running, and there's ripples at the beginning that don't make any sense, in particular that I've labeled anomaly on this graph. So we did a repeat, but first we'll take a close look at this. If we zoom in, it turned out there was an anomaly that appeared where 0 wasn't 0, and it kept doing this, dropping down below 0 and dropping back up. And I don't know what caused that. I never did figure that out. I turned everything off and turned everything back on again, and it went away. And then later in subsequent experiments, it came back again. So I don't know what is going on with that sensor. Consequently, I repeated this experiment. And so in that repeat, this shows 0, steady state running, and then some load. And then I brought the train within proximity and didn't use the small magnet, and everything could remain on the same scale. So that was a successful run of the experiment. Shows the effect of the magnet to be as great or greater, in fact, Magne-Traction several times greater than normal running. So, and I was even more careful not to get the train too close to it. So we did not get closer than 1.5 inches. So Magne-Traction could indeed impact your sensor readings with this type of sensor. To summarize, using current sensors for train detection could probably use either type. However, there's real serious considerations with using some of these sensors. The ACS 712, in my experiments, worked pretty much as described, but for train detection there are some possible issues. I didn't highlight it, but there were only 2 to 3 bits of information between the difference between 0 and a car running with load. That, to my mind, makes the detection of a train a little tenuous, and I'd want to get a sensor with greater sensitivity if I was going to do this with a Hall effect sensor. We obtained an anomalous baseline reading twice in just a few experiments. That's not good, particularly when we have so few bits of information to work with. And then the Magne-Traction greatly impact the reading. So if you're a Lionel fan like I am and you run vintage trains, that could be an issue for you. Also, I have to wonder about the motors, even of a N-gauge train might generate some signal. And a train with no power sitting on a track might be enough to a magnetism to make the things think the train is alive. You have the Max 4080S and the Adafruit INA 169 shunt type sensors that I've experimented with. What we just saw were experiments with the Max 4080S, and these work as described in literature. They're quite a bit more sensitive than the ACS 712. Full scale reading on these sensors out of the box is 1 amp, as opposed to the ACS 712 full scale is 5 amps. So that's one way to decide, a quick way to think about your resolution and the 5 volts you read from an Arduino, for example. So it is more sensitive. Still, not a lot of bit difference because we're measuring really small millivolt differences. And I do prefer the INA 169 because it's easily modified to increase that sensitivity and overcome that issue. Okay, up next we have and look at reed switches. Reed switch is just a simple switch that is triggered by magnetism. So you can use this in various ways. I'm going to talk about how they work in only a few seconds because they are so simple. And then I'll show some examples of how I've used them on my layout. With a reed switch, you can mount it between the rails or alongside the track. And if there's some magnetism, a magnet attached to your train or Magne-Traction wheels, it'll close that switch. And you could sense the closure of the switch using your Arduino very simply. So now we'll do some similar experiments with the reed switch just to show it working and Magne-Traction and a magnet and how that works. We have a LED that's really bright, so at first it doesn't seem like it shows up on the video, but you'll see it when it goes off. That's on until the reed switch is closed by a magnet. Now we can demonstrate that. Taking a tiny magnet, putting it in proximity, and there it goes. And (1950s) Magne-Traction engine with Magne-Traction. Put the wheel near, and the light goes out. Okay, up next we have some examples from my layout. I hope you enjoy those. The first one that uses reed switches is an under-table robot that fetches the logs from my sawmill after they've been dumped. It goes under the table, goes under the sawmill, then with a servo opens the sawmill door and then comes back. The thing that it knows where it is because of reed switches between the rails on this track. Next up, we have the train running on the track. We've got a couple. We got sound triggered. So sound is triggered by the reed switches. Also, because I've got two mounted on the track, I can tell speed and direction of the train. So I have a known scale distance between the closure of reed switch 1 and 2, so I can see 39 miles an hour heading to the city. And so that's a relatively simple calculation that Arduino Uno under the table is doing that. There it comes around again. And now it does 2 and 3, so I know the direction. And again, because they're a scale distance apart, I can calculate the speed. So that's scale speed, obviously. And that's just a signal tower guy is also triggered by the reed switches. When I go toward the city, he goes back in, and when I come into that yard, he comes out. I also use reed switches on the switches so I can tell if a siding is open or closed. And so if I open that siding we just looked at, it tells this little nano Arduino that siding is open and then close, and that's done by a reed switch. So that says do not enter. That number is actually coming from a range finder in the back that's saying how many scale feet the end of that those train cars are from the end. So we're just going to look at how this works. The silver thing is the magnet, and the black thing is the reed switch. I hit the wrong button at first. That's why you heard the click before. There you go. So there we go. It's open. In this case, that is when the reed switch is closed. Now the reed switch is open, so now the siding is closed. Do not enter. No entry, it says. All right, so there's summary. They're really inexpensive, probably less than $1 if you want to shop around a little. Very versatile. You can put them in lots of different places, and you can have a ton of fun with them. I mean, what's fun about it is getting a pack of little magnets, and you can put it on all sorts of stuff and know where they are, or that sort of thing. As I demonstrated, you could use 2 of them to calculate speed and direction of your train. And they're very simple to wire. They're just 2 wires. Right? They don't need any power. So one end goes to ground, one end goes to a pin that you sense on the Arduino. And of course, the code is relatively simple. I should mention, of course, that the code may require some debounce. For example, if you have a magnet on all your trains in the same location, and some of your trains have Magne-Traction and some don't, then you might want to have some code to detect the train only once. And that's what I mean by debounce. We talked a little bit, so this is our summary. We talked a little bit about light-based sensors. They're considerably more expensive than anything we talked about here. You could make them cheaper by building them yourself. That should not be too difficult. I built a pair. These did require quite a bit more coding to use, but they worked for years without any fails that I know of. So it's certainly a possible way to go, but they're much more disruptive to the track. Current sensors and reed switches are easy to code. They're easily installed on your layout. Reed switches are very inexpensive. especially compared to current sensors. But I also think the reed switches have a lot of versatility in detecting things, not just trains, but other things. And because they're cheap, you can deploy them in numerous places around your layout. So I do think that's an advantage. A current sensor certainly would work fine, and maybe that's even less disruption to your layout if you're just splicing into some wires. And the rest of the video, it's regarded to the code and that I used in these experiments. This is all the code that was used. It ran on an Arduino Uno. The setup code is straightforward. We establish the input and output pins, and we basically are using 3 pins. We use one to read the reed sensor. We use one to turn on an LED or turn off an LED, and then we use one for the current sensor. So I had to move the wires from one to the other when I did the test, and you'll see I made some other changes. Just to go toward the bottom first, there's a define section at the bottom that is all the code difference between the two sensors. If you use this code for your own experiment, you basically, to switch between the sensors, you uncomment one line, and then the if-def takes care of the rest. Otherwise, there's at the top, there's the loop. The loop reads the reed sensor, and if the reed sensor is closed, it turns the LED off. Otherwise, the LED remains on. And then we take a bunch of readings from our current sensor and we average those, and then we calculate voltage and current and print that out. And the graphs that you saw were all generated simply by using the serial plotter in the Arduino IDE. So this code generates those print statements. The serial plotter in the Arduino IDE generated the graphs. And that's all there was to that. Well, I hope you enjoyed this video. I had fun making it, and it came out much longer than I expected, but hopefully that aspect won't turn you off. I promise to get more succinct in the future. Thank you. Please subscribe if you want to catch my videos that will come out probably not until next year. Well, I should say next season, because it'll probably be in the fall. Thank you. Bye.